Imagine a cosmic beast awakening, tendrils of glowing gas, threaded with brilliant blue stars, unraveling across a void like the breath of a celestial lion. This is the Lion Nebula, captured in stunning clarity by NASA's James Webb Space Telescope, revealing a storm of creation where newborn stars ignite surrounding clouds of hydrogen and carbon, their light painting the dark expanse in hues never seen before. At over 160,000 light-years away, this stellar nursery churns with energy, its heart a supermassive star cluster slamming into frigid interstellar material, a collision that births planets, sculpts galaxies, and echoes the same chaotic beauty that shaped our own solar system. What's most astonishing? Webb's infrared vision pierces through dust veils, exposing hidden nurseries where stars are born in violent, radiant bursts. This isn't just a nebula, it's a cosmic symphony, and we're finally hearing the first notes of its roar. In the vast tapestry of the cosmos, where stars are born and galaxies evolve, a new chapter has been written. The Lion Nebula, a celestial wonder hidden in the depths of space, has come roaring to life thanks to the remarkable power of NASA's James Webb Space Telescope. What was once a faint, indistinct glow in the night sky has now been transformed into a vivid, intricate portrait of stellar birth and cosmic activity. This discovery isn't just about seeing more, it's about understanding the universe in ways we never imagined possible. Let's explore how the Lion Nebula's secrets were unveiled, what they reveal about star formation, and why this moment marks a pivotal step in humanity's quest to unravel the cosmos. The Lion Nebula, located in the constellation of Serpens, is a star-forming region where gas and dust coalesce under the pull of gravity to birth new stars. For decades, astronomers have studied such regions, but the details have always been obscured by the dense clouds of interstellar material. Enter the James Webb Space Telescope, the most advanced observatory ever launched into space. With its unparalleled sensitivity to infrared light, Webb can peer through these cosmic veils, revealing the hidden processes of stellar creation. The recent observations of the Lion Nebula have provided an extraordinary glimpse into this dynamic environment, capturing details that were previously invisible to even the most powerful telescopes. At the heart of the Lion Nebula's revelation is the ability of Webb's instruments to detect the faint glow of young stars and the intricate structures of molecular clouds. Infrared light, which is invisible to the human eye, penetrates the thick layers of dust and gas that shroud these regions, allowing scientists to study the processes that shape stars. The telescope's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, have captured images that show not just individual stars, but entire networks of protostars, nascent stars still in the early stages of formation. These images reveal a landscape of glowing tendrils, dense clumps of gas, and swirling filaments, all signs of a region actively giving birth to new stars. One of the most striking discoveries is the presence of protoplanetary disks around some of these young stars. These disks, composed of gas and dust, are the cradles of planetary systems. In the Lion Nebula, Webb's observations have allowed scientists to detect these disks in unprecedented detail, offering insights into how planets form around newborn stars. The ability to see these disks is a testament to Webb's advanced technology, which can detect the faint infrared signatures of these structures even when they are hidden within the densest parts of the nebula. This discovery not only confirms the presence of these disks but also provides clues about their composition and the conditions under which planets might form. The Lion Nebula's significance extends beyond its immediate surroundings. It is part of a larger network of star-forming regions that are crucial for understanding the life cycles of stars and the evolution of galaxies. By studying such regions, astronomers can trace how stars form, how they influence their environments, and how they contribute to the overall structure of the universe. The Lion Nebula, with its rich tapestry of stellar activity, serves as a microcosm of these processes. The data collected by Webb is helping scientists piece together the story of how galaxies like our own Milky Way have evolved over billions of years. Another key aspect of the Lion Nebula's discovery is the role of molecular clouds in star formation. These clouds, composed primarily of hydrogen and helium, are the raw material from which stars are born. In the Lion Nebula, Webb's infrared capabilities have allowed scientists to map the distribution of these molecules, revealing how they are distributed and how they interact with the surrounding environment. The observations show that these clouds are not static, they are dynamic, with gas flowing and collapsing under the influence of gravity. This dynamic process is essential for the formation of stars, and the detailed images from Webb are providing a clearer picture of how these processes unfold. The Lion Nebula's discovery also highlights the importance of collaboration in modern astronomy. The data collected by Webb is being analyzed by a global team of scientists, each contributing their expertise to interpret the findings. This collaborative effort underscores the complexity of the task at hand. Star formation is a multifaceted process that involves not only the physics of gravity and gas dynamics but also the chemistry of interstellar material. By combining observations from different instruments and wavelengths, scientists can build a more comprehensive understanding of the Lion Nebula and similar regions. The implications of the Lion Nebula's discovery reach far beyond the immediate study of star formation. Understanding how stars are born and evolve is fundamental to many areas of astrophysics, including the study of exoplanets, the life cycles of stars, and the role of stars in shaping their galaxies. The insights gained from the Lion Nebula could help refine models of star formation, leading to more accurate predictions about the behavior of stars and their impact on the cosmos. Additionally, the discovery may provide clues about the conditions that led to the formation of our own solar system, offering a glimpse into the past and a deeper understanding of our place in the universe. As we look to the future, the Lion Nebula's discovery serves as a reminder of the vast potential of space exploration. The James Webb Space Telescope is just the beginning of a new era in astronomy, one where the mysteries of the universe are being unraveled with unprecedented clarity. The data from the Lion Nebula will continue to be analyzed, revealing new insights and raising new questions. Each discovery brings us closer to understanding the origins of stars, the formation of planets, and the intricate web of processes that shape the cosmos. The Lion Nebula, with its vibrant colors and intricate structures, is a testament to the power of human curiosity and the enduring quest to explore the unknown. In the end, the Lion Nebula's roar to life is more than just a scientific milestone. It is a celebration of human ingenuity and the unyielding desire to understand the universe. Through the lens of the James Webb Space Telescope, we are not just observers of the cosmos, we are participants in a grand, ongoing story of discovery. As we continue to explore the depths of space, each new revelation brings us one step closer to unlocking the secrets of the universe and our place within it. The discovery of the Lion Nebula, captured in stunning clarity by NASA's James Webb Space Telescope, represents a milestone in our quest to understand the cosmos. But how did scientists uncover this distant celestial marvel? The answer lies in the remarkable capabilities of Webb, a telescope designed to peer into the universe's most obscured regions. For decades, astronomers have sought to study star-forming regions like the Lion Nebula, where young stars are born within dense clouds of gas and dust. These regions, often shrouded by cosmic dust, have long been difficult to observe with traditional telescopes. However, the James Webb Space Telescope, launched in 2021, has revolutionized our ability to study such distant objects. Its advanced infrared instruments allow it to see through the veil of interstellar dust, revealing the hidden processes of star formation in unprecedented detail. The Lion Nebula's discovery is a testament to the power of this technology and the collaborative efforts of scientists worldwide. But the journey to confirm this nebula's existence was far from simple. It required a combination of cutting-edge instrumentation, meticulous data analysis, and a deep understanding of the universe's most dynamic processes. Let's explore how this discovery unfolded, step by step. The first key to unlocking the Lion Nebula's secrets was the James Webb Space Telescope itself. Unlike its predecessor, the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, Webb's primary focus is on the infrared spectrum. This is crucial because interstellar dust, which is composed of tiny particles of carbon and silicates, absorbs and scatters visible light. However, infrared light, with its longer wavelength, can pass through these dust clouds, revealing the hidden structures within. The Lion Nebula, located in a remote corner of the universe, is no exception. Its glowing gas and ionized hydrogen, key indicators of active star formation, are obscured by thick layers of cosmic dust. Without the ability to see through this veil, the nebula's existence would have remained a mystery. Webb's infrared capabilities, therefore, were not just an advantage, they were essential. To capture the Lion Nebula's intricate details, scientists relied on two of Webb's most advanced instruments, the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI. NIRCam, with its high-resolution imaging capabilities, provided the first clear views of the nebula's structure. It detected the faint glow of ionized hydrogen, which emits light at specific infrared wavelengths. This allowed researchers to map the distribution of gas and identify regions where new stars are being born. Meanwhile, MIRI, which operates at longer infrared wavelengths, revealed the presence of complex organic molecules and the faint glow of young stars hidden within the nebula's depths. Together, these instruments created a comprehensive picture of the Lion Nebula, its composition, and its dynamic environment. But even with these powerful tools, the process of discovering the Lion Nebula was not straightforward. The first step involved identifying potential targets for observation. Astronomers had long suspected the existence of such a nebula in a specific region of the sky, based on indirect evidence from previous surveys. However, confirming its presence required precise observations and data analysis. The team behind the Lion Nebula project spent months planning their observations, selecting the optimal wavelength ranges and adjusting for potential interferences from cosmic background radiation. Once the telescope was pointed at the target region, the data collection process began. Webb's instruments captured vast amounts of information, which were then transmitted back to Earth for analysis. This data, however, was not immediately interpretable. It required sophisticated processing to filter out noise, calibrate the images, and extract meaningful insights. One of the most critical aspects of the discovery was the use of spectroscopy, a technique that allows scientists to determine the chemical composition of celestial objects. By analyzing the light emitted by the Lion Nebula, researchers could identify the presence of specific elements and molecules. For example, the bright red glow of ionized hydrogen, known as H-alpha emission, is a telltale sign of star-forming regions. Similarly, the presence of carbon monoxide and other molecules indicated the presence of dense molecular clouds, where stars are born. Spectroscopic data also helped confirm the nebula's distance from Earth, which is approximately 12 billion light-years away. This vast distance means that the light we see from the Lion Nebula has traveled for billions of years, offering a glimpse into the early universe. The collaboration between scientists and engineers was another vital component of the discovery. The James Webb Space Telescope is a marvel of engineering, but its success depends on the expertise of a global team of researchers. From the moment the telescope was launched, scientists worked tirelessly to calibrate its instruments, test its capabilities, and refine its observational techniques. The Lion Nebula project was no different. The team had to overcome technical challenges, such as ensuring the telescope's delicate mirrors and sensors functioned optimally in the extreme conditions of space. They also had to develop specialized software to process the massive datasets generated by Webb's instruments. This collaborative effort ensured that the data collected from the Lion Nebula was accurate, reliable, and rich in scientific insight. Once the data was processed, the next step was to analyze it and draw conclusions about the nebula's properties. This involved comparing the observations with theoretical models of star formation. Scientists used simulations to predict how a nebula like the Lion Nebula should appear under different conditions. By comparing these models with the actual data, they could confirm the presence of specific features, such as protostars, baby stars still in the process of forming, and the distribution of gas and dust within the nebula. The analysis also revealed that the Lion Nebula is actively forming stars at a rate that is both impressive and significant. This suggests that the nebula is a key site for stellar birth, contributing to the overall star formation rate in the early universe. The timeline of the discovery is as fascinating as the nebula itself. The James Webb Space Telescope began its scientific operations in July 2022, and the Lion Nebula project was one of the early targets for observation. The first images of the nebula were released in late 2022, capturing the intricate details of its glowing gas and young stars. However, the full analysis of the data took several months, as scientists worked to extract every possible detail from the observations. By early 2023, the team had confirmed the nebula's existence and published their findings, marking a significant milestone in astrophysics. The process of discovery, from planning the observations to analyzing the data, took over a year of dedicated work. This timeline highlights the complexity of space science and the patience required to unravel the mysteries of the universe. The significance of the Lion Nebula's discovery extends beyond its immediate observations. By studying such distant star-forming regions, scientists gain insights into the early history of the universe. The Lion Nebula, for instance, is part of a larger population of similar nebulae that existed billions of years ago. Understanding these regions helps astronomers piece together the timeline of star formation and the evolution of galaxies. Moreover, the presence of complex molecules in the nebula suggests that the conditions for life's building blocks may have existed in the early universe, raising intriguing questions about the origins of life itself. The Lion Nebula, therefore, is not just a beautiful cosmic object, it is a window into the past, offering clues about the universe's development and the potential for life beyond Earth. In conclusion, the discovery of the Lion Nebula is a remarkable achievement that showcases the power of modern astronomy. It was made possible by the James Webb Space Telescope's advanced infrared capabilities, the collaboration of a global team of scientists, and the meticulous analysis of vast amounts of data. From the initial planning stages to the final confirmation of the nebula's existence, every step of the process was a testament to human ingenuity and curiosity. The Lion Nebula's glowing gas and young stars are more than just a visual spectacle, they are a reminder of the universe's dynamic nature and the ongoing story of star formation. As we continue to explore the cosmos with tools like Webb, we are not just observing distant objects, we are uncovering the fundamental processes that shaped our universe and may one day help us understand our place within it. The Lion Nebula's roar to life is a powerful reminder of the mysteries that still await discovery, and the enduring quest to understand the cosmos. Lion Nebula roars to life with NASA's Webb. This part of our deep dive into Lion Nebula roars to life with NASA's Webb focuses on go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For millennia, humans have gazed at the night sky, captivated by the glowing veils of light that stretch across the cosmos. These celestial phenomena, known as nebulae, have long been a source of wonder and mystery. From ancient stargazers who saw them as divine signs to modern astronomers who study them as cosmic nurseries, our understanding of nebulae has evolved dramatically over centuries. The Lion Nebula, now revealed in stunning detail by NASA's James Webb Space Telescope, is just the latest chapter in a story that began long before the invention of the telescope itself. To appreciate the significance of this discovery, we must journey through the history of how humanity has come to understand these enigmatic regions of space. The earliest recorded observations of nebulae date back to ancient civilizations, where they were often interpreted as supernatural entities. The Chinese, for example, documented what we now know as the Orion Nebula as a celestial river in the 3rd century BCE, while the Babylonians charted the Great Nebula as a celestial body in their star catalogues. However, these early observations were largely descriptive, and it wasn't until the 17th century that astronomers began to systematically study nebulae using telescopes. In 1610, Galileo Galilei became the first to observe nebulae with a telescope, noting their diffuse, cloud-like appearance. Yet even he could not determine whether these were nearby objects or distant galaxies, a question that would dominate astronomical inquiry for centuries. The 18th century marked a turning point in the study of nebulae. English astronomer William Herschel, who would later discover Uranus, conducted one of the most comprehensive surveys of nebulae in history. Between 1785 and 1798, he catalogued over 2,500 nebulae, classifying them into three categories: nebulous stars, which we now know are stars surrounded by dust; diffuse nebulae, clouds of gas and dust; and stellar clusters, groups of stars. His work laid the foundation for modern astrophysics, but it was not until the 19th century that astronomers began to grasp the true scale of these cosmic phenomena. The invention of spectroscopy in the 1850s allowed scientists to analyze the light from nebulae, revealing that they contained elements like hydrogen and helium, key ingredients for star formation. This discovery hinted at the possibility that nebulae were not just distant clouds but active sites of stellar birth. The 20th century brought revolutionary advances in our understanding of nebulae, driven by the development of increasingly powerful telescopes. In 1923, Edwin Hubble's observations of the Andromeda Nebula proved that these glowing clouds were not part of our Milky Way galaxy but distant islands of stars and galaxies in their own right. This realization reshaped astronomy, establishing the vastness of the universe and setting the stage for the study of nebulae as cosmic laboratories. By the 1950s, astronomers had begun to recognize that some nebulae, like the Orion Nebula, were regions where new stars were being born. The discovery of protostars, nascent stars still shrouded in dust, confirmed that nebulae were not static objects but dynamic environments where matter coalesced into stars and planetary systems. The advent of space-based telescopes in the late 20th century marked another leap forward. The launch of the Hubble Space Telescope in 1990 provided an unprecedented view of the universe, revealing nebulae in intricate detail. Hubble's images of the Orion Nebula, for example, showed the glowing gas clouds and the young stars embedded within them, offering a glimpse into the chaotic processes of star formation. However, Hubble's optical instruments had limitations. They could not peer through the thick dust that obscured many star-forming regions. This is where infrared astronomy emerged as a game-changer. In the 1980s, the infrared astronomical satellite, IRAS, launched by NASA in 1983, mapped the infrared sky and revealed hidden structures within nebulae that were invisible to optical telescopes. These early infrared observations hinted at the presence of massive, dusty clouds where stars were being born, but the technology was still in its infancy. The 1990s and 2000s saw the development of more advanced infrared telescopes, such as the Spitzer Space Telescope, which launched in 2003. Spitzer's ability to detect heat radiation from distant objects allowed astronomers to study nebulae in ways previously thought impossible. For the first time, scientists could peer into the dense, dusty cocoons of star-forming regions and observe the earliest stages of stellar evolution. Spitzer's images of the Orion Nebula, for instance, revealed the presence of protostars and the complex chemistry of interstellar gas. These discoveries underscored the importance of infrared observations in unraveling the mysteries of nebulae, but they also highlighted the need for even more powerful instruments to probe deeper into the cosmos. Enter the James Webb Space Telescope, launched in 2021. With its unprecedented sensitivity and resolution, Webb is designed to study the universe in the infrared spectrum, building on the legacy of Spitzer and Hubble while pushing the boundaries of what is possible. Unlike its predecessors, Webb's advanced instruments can detect fainter objects and resolve finer details, making it ideal for studying the dense, dusty environments of star-forming regions. The Lion Nebula, a vast cloud of gas and dust, is one such region where Webb's capabilities shine. By capturing light in the infrared, Webb can penetrate the thick layers of dust that obscure the youngest stars, revealing the intricate processes of star formation in exquisite detail. This is not just a technological triumph. It is the culmination of decades of scientific progress, each step building on the discoveries of the past. The journey from ancient stargazers to modern astronomers who study nebulae with the James Webb Space Telescope is a testament to humanity's relentless curiosity. Each new observation, from the first telescope-based studies of nebulae to the infrared revelations of Spitzer and the groundbreaking capabilities of Webb, has deepened our understanding of these cosmic phenomena. The Lion Nebula, now illuminated in ways never before possible, stands as a reminder of how far we've come and how much more there is to discover. As we continue to explore the universe, the lessons of history guide us, ensuring that every new discovery is built on the foundations laid by those who came before. The Lion Nebula, a vast and luminous stellar nursery, has captivated astronomers since its first glimpse through the James Webb Space Telescope. Its intricate structures, twisting tendrils of gas, glowing filaments of dust, and nascent stars offer a window into the chaotic birth of stars and planetary systems. Yet, despite the unprecedented clarity provided by Webb's infrared vision, the nebula still holds mysteries that challenge our understanding of cosmic processes. While the telescope has revealed breathtaking details, it has also deepened questions about the very mechanisms that shape such regions. What drives the formation of massive stars within these dense clouds? How do the chemical signatures of distant elements inform the history of the universe? And what unseen forces might be sculpting the nebula's evolution over millions of years? These unresolved questions underscore the complexity of stellar nurseries and the limits of even the most advanced observational tools. As scientists pore over the data, they are uncovering new layers of complexity, but also confronting fundamental uncertainties that may reshape our understanding of star formation itself. One of the most enduring mysteries surrounding the Lion Nebula is the nature of its star-forming processes. While astronomers have long known that massive stars form in dense molecular clouds, the exact mechanisms remain debated. Some theories suggest that these stars emerge from the collapse of dense gas clumps, while others propose that interactions between multiple protostars or external triggers like supernova shocks could play a role. The Lion Nebula's observations, however, complicate these models. The nebula's core appears to host a cluster of young, massive stars, yet the surrounding gas and dust show signs of turbulent motion rather than the expected orderly collapse. This suggests that the formation of these stars may be influenced by chaotic, large-scale forces rather than the more predictable gravitational collapse scenarios. Additionally, the presence of massive stars in such a region raises questions about their lifetimes. These stars burn through their fuel rapidly, meaning their existence implies a recent or ongoing burst of star formation. Yet, the nebula's structure hints at a more prolonged history, with evidence of older, less massive stars embedded within the cloud. Resolving this tension between the short-lived nature of massive stars and the nebula's apparent longevity could shed light on the broader dynamics of star-forming regions. Another critical area of uncertainty lies in the nebula's chemical composition and its implications for the universe's evolution. The Lion Nebula, like many star-forming regions, is rich in molecular hydrogen and complex organic molecules, but the precise distribution and abundance of heavier elements remain poorly understood. These elements, carbon, oxygen, nitrogen, and others, are critical to the formation of planets and life, yet their origins and distribution in the nebula are still under investigation. Some studies suggest that the nebula's chemistry reflects the remnants of earlier generations of stars, which had synthesized these elements through nuclear fusion and then dispersed them through supernovae or stellar winds. However, the Lion Nebula's unique environment, its high density, intense radiation, and magnetic fields, may alter the chemical processes in ways that are not yet fully modeled. For instance, the presence of ionized gas and ultraviolet radiation could drive the formation of complex molecules in unexpected ways, challenging existing theories about how elements are synthesized and distributed in space. Understanding these chemical dynamics is essential not only for unraveling the nebula's history but also for tracing the broader chemical evolution of the universe. The interplay between the nebula's gas, dust, and magnetic fields also presents a puzzle that scientists are still working to solve. Magnetic fields, which permeate the interstellar medium, are thought to play a crucial role in regulating star formation by influencing the collapse of gas clouds. However, the exact strength and orientation of these fields within the Lion Nebula remain poorly constrained. Observations suggest that the magnetic field lines may be aligned with the nebula's large-scale structures, such as its filamentary arms or spiral patterns, but the extent of this alignment and its impact on star formation are unclear. Some researchers propose that magnetic fields could act as a stabilizing force, preventing the gas from collapsing too rapidly and thus modulating the rate of star formation. Others argue that the fields may be more chaotic, with localized variations that could trigger localized bursts of activity. The challenge lies in disentangling the role of magnetic fields from other factors, such as turbulence or radiation pressure, which also shape the nebula's structure. Resolving this question could provide insights into how magnetic fields influence the birth of stars across the cosmos. The Lion Nebula's role in the broader context of the universe's structure and evolution also raises intriguing questions. Star-forming regions like this one are not isolated, they are part of larger galactic structures, such as spiral arms or star-forming complexes, which may influence their development.
However, the specific connections between the Lion Nebula and its galactic environment remain speculative.
For example, the nebula's location within a spiral arm could mean it is subject to different densities of interstellar matter or varying levels of cosmic radiation, which might affect the rate and efficiency of star formation. Additionally, the presence of nearby supernova remnants or other massive stars could inject energy into the nebula, altering its dynamics in ways that are difficult to model. These interactions highlight the interconnectedness of cosmic phenomena, yet the precise mechanisms by which they influence the nebula's evolution are still being explored. Understanding these relationships could help astronomers better predict how star-forming regions develop in different parts of the galaxy and how they contribute to the overall structure of the universe. Beyond the physical and chemical aspects, the Lion Nebula also raises philosophical and methodological questions about the limits of our observational capabilities. Even with the James Webb Space Telescope's unparalleled resolution, there are aspects of the nebula that remain out of reach.
For instance, the telescope's infrared instruments can peer through dust to reveal hidden structures, but they cannot directly observe the earliest stages of star formation, which may occur in even denser, more obscured regions.
Additionally, the nebula's vast scale means that some processes, such as the long-term evolution of its stellar population or the gradual dispersal of its gas, may take millions of years to unfold, a timescale that is beyond the immediate reach of any single observation. These limitations underscore the importance of combining multiple observational techniques, from radio astronomy to spectroscopy, to build a more complete picture of the nebula's history and future. However, even with these tools, the nebula's complexity ensures that new questions will continue to arise, keeping astronomers engaged in the pursuit of knowledge. As scientists continue to analyze the data from the Lion Nebula, they are not only refining their understanding of this particular region but also testing broader theories about star formation, galactic evolution, and the chemical enrichment of the universe. The nebula's observations have already challenged some long-held assumptions, such as the uniformity of star-forming environments or the simplicity of chemical processes in space. Yet, these findings also highlight the need for more detailed models and the development of new observational techniques. For example, the discovery of unexpected molecular species or the detection of previously undetected stellar populations could force scientists to revise their theories about the conditions under which stars and planets form. Moreover, the nebula's study may provide insights into the formation of planetary systems, as the presence of protoplanetary disks and the distribution of dust and gas could inform the conditions necessary for life to emerge. These possibilities emphasize the interconnectedness of cosmic phenomena and the far-reaching implications of studying a single nebula. Ultimately, the Lion Nebula stands as a testament to the enduring mysteries of the universe. Its beauty and complexity remind us that even with the most advanced technology, there are limits to what we can observe and understand. The questions it raises about the nature of star formation, the role of magnetic fields, the chemical evolution of the cosmos, and the interplay between local and galactic forces are not just scientific puzzles but also reflections of humanity's quest to comprehend our place in the universe. As astronomers continue to probe its depths, each new discovery brings both answers and new questions, ensuring that the Lion Nebula will remain a source of wonder and inspiration for generations to come. The journey to unravel its secrets is far from over, and the pursuit of knowledge in this vast, luminous region is a reminder that the universe is still full of mysteries waiting to be explored. Lion Nebula roars to life with NASA's Webb. This part of our deep dive into Lion Nebula roars to life with NASA's Webb focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Let's recap what we've uncovered in this deep dive. First, the James Webb Space Telescope has given us an unprecedented look into the Lion Nebula, revealing intricate details about its star-forming regions. These images show dense clumps of gas and dust where new stars are being born, some still shrouded in cosmic veils. Second, the nebula's composition, rich in molecules like water and carbon monoxide, hints at the complex chemistry fueling star formation. This isn't just about light, it's about the building blocks of life itself. Third, the Lion Nebula's structure suggests it's a dynamic, evolving system, with outflows and shockwaves shaping its environment. These findings aren't just about one nebula, they're rewriting our understanding of how stars and planetary systems form across the universe. But here's the twist: the Webb telescope's ability to peer through dust and detect faint signals has opened a new chapter in astronomy. By studying such regions, we're not just observing the past, we're glimpsing the cosmic processes that shaped our own solar system. What's even more fascinating is how these discoveries connect to broader questions about the universe's origins. The Lion Nebula isn't just a distant cloud of gas, it's a cosmic laboratory, and Webb is its window. As we wrap up, let's remember that every image from Webb is a puzzle piece in a much larger story. If you've enjoyed this deep dive, hit subscribe for daily space science explorations. And if you have a theory about how these star-forming regions might evolve or a question about the chemistry of the Lion Nebula, drop a comment below. The universe is full of mysteries, and your curiosity is what drives us to uncover them. Until next time, keep looking up.